Dear friends, hello and best wishes for good health and prosperity in all respects. The title of this video is Interpretations and Directions of Development in Quantum Physics and Modern Science. First, some relatively well-known general findings, then something newer and hopefully interesting in this video and the next one. One of the most famous creators of quantum physics, Werner Heisenberg, in his famous book Physik und Philosophie, sometimes quoted as Physics und Metaphysics, wrote that the most fruitful development in the history of human thought occurs at the point where two different lines of thought intersect. In the distant year 1687, Newton's famous Philosophiae Naturalis Principia Mathematica was published. Pierre Simon de Laplace, the Marquis, rightly fascinated by the work, exclaimed in his book Celestial Mechanics, La Mécanique Céleste, "Give me sufficiently precise and powerful instruments and a mathematical model sufficiently strong, and I will predict how the universe will behave thousands of years ahead, and I could say what it was like 100 years ago." But is it so? Chaos theory has shown that a powerful mathematical relation is not enough, and that a slight change in a control parameter can cause dramatic changes in the dynamic flow of the system. This is called the butterfly effect, metaphor given by Lorentz, one of the originators of the theory that a butterfly in Hong Kong can cause a storm in New York. Heisenberg's uncertainty principle showed that even sufficiently precise instruments are not enough, and that uncertainty is an inherent property of things independent of our measurement capabilities. We will either have the position of a particle exactly determined or the momentum. In the photo, Heisenberg depicted is from Breaking Bad, but of course the real Heisenberg is Werner of Bavaria. To this we could add Kurt Gödel, who showed that even logic is not enough. His incompleteness theorem stated that when a robot, in other words a formal logical system, becomes so sophisticated, consistent and complete, that it becomes able to create statements about statements or mathematics about mathematics, circular or self-reference statements, in other words, a robot able to say I, myself. At this point, we arrived at insoluble propositions. Gödel was Einstein's favorite colleague with whom he communicated at Princeton. I have been there. I discuss Gödel's law of incompleteness at length in my video Charles Berner's Lila Paradigm, interview with Biljana Percinkova by Satyen Raja and Caroline Thompson, in duration of 1 hour and 35 minutes. Also in my video on general relativity and Einstein's field equations, which is 2 hours and 7 minutes long. Based on all this, we can conclude that there is a clear crisis of interpretations in modern science, especially in quantum physics, and the logic on which it is based. Thus, based on the interpretation of the basic relation in quantum physics, which is the probabilistic Schrödinger wave equation, we can recognize at least 6 different directions of interpretation. Here I presented them in different colors with their originators, and in each of them there is a genius practically. So, whichever branch we choose, we will find ourselves in a good company. Here we see Einstein, we see Bohr, von Neumann, and Charles Werner. The fundamental problem in quantum physics that has led to a crisis of interpretation can be most simply formulated as follows. We have to perform certain measurements in a given quantum system. We carry out the measurements on certain physical magnitudes, variables, which are also called observables, precisely because of the possible influence of the observer on them. We call the variables observables. We will see that this is precisely where the fundamental controversy comes from in this science, which has the ambition, not at all modest, to explain the deepest essence of the world in which we live and whose product we ourselves are. The possible results of the measurements are limited to a set of omega variables represented by real numbers. Simply, we can state probability of A to belong to a set omega for a quantum system C equals P. Or the equation simply says there exists a certain probability P, some P, out of the set of possible values omega in a given quantum system C to obtain by measurement the value A. Or stated in another way, in the quantum state C, the probability of finding the value of A to belong to omega is P. What does this mean? Did this value A exist without us as observers, or did we ourselves influence the measurement to get exactly this value? Do all values of omega exist simultaneously, or do they not exist? And why do we obtain the value only with a certain probability and not exactly? This flowchart I have compiled illustrates the most important branches and interpretations of this maybe most important science of the 20th century. It is not at all simple to decide on one or another direction of thinking. We can be comforted by the fact that in practically every branch, like I said, there is one genius, physicist, or Nobel laureate. Why are the results we obtain probabilistic, that is, given with a certain probability and not exactly determined? Let's remember that Einstein did not agree even with this. He said, God does not play dice. In other words, I'm convinced that there must be a way to represent things in the universe in a deterministic, precise way and not by their probabilities. He did not agree with another postulate in quantum physics, namely that the observer acts on and influences the observed. We will see later that these two postulates, the probabilistic character of the results in quantum physics and the possible influence of the observer, are actually linked. I cannot agree that the mouse influences the universe just because it observes it, was Einstein's position on this matter. We mentioned that the dispute between Einstein and Bohr lasted more than half a century. It is remembered that at the time of Bohr's funeral, a sketch of Einstein's Gedanken, that means thought experiment, still stood on his blackboard. The old physicist, Bohr, remained obsessed with his great opponent until his last hour. He said, "How is it that Einstein finds it difficult to accept the influence of the observer on the observed when he himself created the theory of relativity from which it results that the time is relative and dependent on the state of motion of the observer? Quantum mechanics is a natural extension of his own theory." To this, Einstein replied that a good joke can only be made once. A good joke is not done twice. So, what are the possible interpretations and orientations in quantum mechanics? Is consciousness involved, and in what way the consciousness as an ontological category is included in this strict scientific branch resulting from materialism as a worldview? On the flowchart, we see that the first and basic question we can ask ourselves is measurement a problem in science? Two answers are possible, yes and no. Classical physics considers measurement not to be a problem in a way that it is taken into account in a precisely defined, predictable, and mathematically founded way. There is another branch of interpretation of quantum phenomena, which does not consider measurement, that is to say, the experiment, to be an essential problem. These are the adepts of quantum logic. They say Everything is fine with quantum mechanics. What is not fine is that we don't know how to think in a quantum logical way. We have yet to develop a way of thinking that will allow us to understand quantum phenomena as completely natural and normal. John von Neumann belongs to this group. Quantum logicians believe that what George Boole did over a century ago for something that is in the very foundations of computing today should be done for quantum physics today. He created new logic. Let us recall that the English mathematician George Boole, born symbolically in 1815, the year of Waterloo, which signifies the victory of Britain, lived at a time when Europe was the center of all the most significant scientific events. This is especially true of mathematics, in which great names like Gauss, Weierstrass, Cauchy, Lagrange, Kronecker, Sonia Kovalevsky, and others ruled. The island, Britain, was isolated, but in Boole's case, it was this very isolation that bore significant fruit. He created something entirely new. Boole succeeded in creating a new algebra in which he also presented logic strictly mathematically, using the basic logical operators and, or, and not. Modern computer technology and robotics are unthinkable without them. Let's go back to our flowchart. Despite the elegant attitude of quantum logicians, there are a myriad of clues that perhaps measurement is a problem after all. Let's follow the yes branch that claims exactly this. If we agree that measurement is a problem, the next question that arises is measurement an interaction? Is measurement a problem because it is an interaction between a conscious observer and what is observed? No, say some, yes, others. In one branch are David Bohm and Paul Davies. Niels Bohr is in the other. Interactionists, those who claim that measurement must be an interaction with the conscious observer, are certainly interesting. About this in the next video about the quantum eraser, where we could see that this might not be the case, that measurement is an interaction with the conscious observer and that consciousness is involved. This in the next video. But Bohm's attitude does not leave us in the least bit indifferent, and there is more than one reason for that. Let's trace the no branch first. If we agree that measurement is a problem, but it is not an interaction with a conscious observer, there is still a chance that quantum physics might be complete. So the next question we ask is quantum physics complete? No, says Bohm, a physicist whom many place side by side with Einstein. Quantum physics is not complete, and what is missing are the so-called hidden variables. It is very interesting and indicative that it was David Bohm, the heretic, the one who communicated with Krishnamurti, the one who developed the theory that the universe is a giant hologram in which each part reflects the whole, the one who saw the dynamics of the universe as a hollow movement in which the microworld is an image of the macroworld, and which thus approached the understanding of Dharmakaya in Buddhism or Brahman in Hinduism. It was David Bohm and not someone else who eventually came up with an entirely materialistic theory of hidden variables. In his scientific bestsellers, Science, Order and Creativity, and his book Wholeness and the Implicate Order, Bohm develops and mathematically grounds the theory which claims that behind explicit disorder there is an implicate, not implicit, order of things on many levels, and that this order is expressed through hidden variables. Let us emphasize once again that David Bohm's order is not only implicit, but it's implicative. So it's not only hidden, but it implies something. There are also scientists, here we think especially of Hew Everett, who believe that with quantum physics everything is in complete order and that even more it is complete. What is wrong is our interpretation. Our interpretation, namely, should be all possible values of the quantum variables of the set omega, which we have not measured, exist, and in parallel universes. This is the so-called Everett's many worlds interpretation. It is surprising that this interpretation is also accepted by Paul Davies, the famous author of the book The Cosmic Blueprint, then also author of the book About Time, which simultaneously means the book about time, but also it means just in time, and the author of the book The Mind of God. This interpretation is called naive realism because it really fully explains the mathematical relation we have stated. The probability for A to belong to omega for a given quantum system C equals P. But it's just as naive. Some call this interpretation uneconomic. No less than Roger Penrose in his famous book The Emperor's New Mind, because it is really not at all economical to imagine that at every moment and for every possible outcome of either event, a parallel universe is created, and that there is a world in which Schrödinger's cat is alive and another one in which that same cat is dead. Finally, we come to the branch that recognizes measurement not only as a problem, but as a special interaction with the observer. And finally, if the measurement is an interaction, there is a possibility that the consciousness of the observer might also be involved in the whole process. Those are interpretations based on consciousness. If the measurement is an interaction with the conscious observer, then the next question to ask is the observer's consciousness involved? For indeed, if I throw a stone and that stone breaks the window, I will not say that the stone broke the window, but I, the consciousness behind it. In other words, if we agree that instruments affect the results of the measurement, we might as well agree that behind the setting of that experiment is the consciousness of the experimenter, of the physicist. Niels Bohr replied, no. He gave his theory of no deep reality. This understanding is part of the famous Copenhagen interpretation of quantum mechanics. Physics even is not a science about things, thought Bohr. Physics is just a way to talk about things. He saw science as a prism through which reality is reflected. Bohr's no deep reality does not mean that there is no reality down there in the subatomic world of quantum physics. It is. This means, first of all, that this reality should not interest us. Quantum physics has huge credibility. It gives definitely correct results. All processing technology is based on quantum physics. Laser technology is based on it. And what happens down there shouldn't worry us. Many warned Bohr against this attitude and believed that this halted the development of science for more than 50 years. They speculate that maybe someone would emerge with the strength and brains to make a breakthrough on what was happening down there. However, no deep reality is a much more subtle understanding than meets the eye. It also means that the position and momentum of the subatomic observable, which change as a result of observation, are not essential properties of a particle anyway. Without us and observers, they do not exist. At the core of Niels Bohr's worldview is his belief in the fundamental indivisibility of things. No deep reality means there are no hidden variables, no planes of existence beyond our reach. Everything is out there for us to see. Let us recall here that Heisenberg's uncertainty principle states that one can determine with a certain precision either the position or the momentum of a subatomic particle, never both at the same time, and that a measure of this is the Planck's constant. Namely, it is valid that delta V times delta X is equal or greater than half the h bar, the Planck's constant. If we want to determine the position of the observable with a given precision, we increase the accuracy by exposing it to a higher frequency monochromatic wave, thus reducing the probability that the particle will fall into the dark part of the wave where it is invisible. In doing so, however, we simultaneously provide more energy of higher frequency and thus change the momentum. There are several reasons why physicists do not incorporate the conscious observer into the theory. Bohr argued that physical instruments, silver bromide, the Geiger counter, bring the measurement to an irreversible act of amplification even without a conscious observer. It appears that new breakthroughs in neuroscience, cognitive engineering, and other related disciplines are nearing the point where they will reveal a complete physical theory that will explain consciousness. A step to the final answer, hasn't that been said too many times already, to no avail? The instruments that lead to an irreversible act of amplifications without the presence of a conscious observer are constructed by a conscious observer. The whole experiment was designed by a conscious observer. Did the stone break the window? In this sense, even Newton's materialistic theory, which speaks subjectively of the objective world, implicitly contains his idea and therefore his consciousness. It is an idealistic view. If cognitive engineering and neuroscience come up with a physical theory that explains consciousness, doesn't quantum physics still have the task as a fundamental theory about the universe to explain the role of consciousness in that material world that is in its own phenomena, in the phenomena of quantum physics itself? Finally, the last branch belongs to the neo-idealists who claim, of course, the observer's consciousness is involved. Moreover, all is consciousness. The material world is just particular manifestations of my consciousness. This is the esse est percipi doctrine of physicist and Bishop George Berkeley, which means to be is to perceive. Esse est percipi. This room, says Berkeley, begins to exist when I enter it. When I leave it, it ceases to exist. Towards the end of his life, Berkeley softened his idealism. Nevertheless, it seems truthful to me to call him and not someone else the great pioneer of this daring branch of quantum physics. Is there a resolution, and what should be our conclusion? Perhaps there is no final resolution yet, but we could say the following. Properties of the material objects could be objective, subjective, contextual, informational. An informational property of something is that because of which that something exists, that particular feature because of which it exists. For example, traffic lights exist to control traffic. Red means stop, green means go, yellow prepare. If Martians come and wanting to know what the traffic light is for, start measuring its size, weight, power consumption, and so on, they will still work with the objective and contextual properties of the traffic light, but not with its informational property. That is what it exists for. Red, stop, green, go. Ancient philosophical manuscripts say that matter exists in order to know itself. Thus, its informational property, that for which it exists, is to know itself, in the sense that it was written on the oracle of Delphi, gnotis auton, know thyself. Therefore, we will deal with informational properties of material objects rather than contextual properties only if we are dealing with the cognitive component of matter. Maybe it's time we shouted "The Emperor is naked," as Roger Penrose did in his bestseller The Emperor's New Mind, which alludes to the fairy tale The Emperor's New Clothes. He said the emperor is naked. And this cry refers to the necessity of consciousness as an ontological category to maybe enter science. About this in the next video, which will elaborate the quantum eraser and the experiment with the bomb. Until then, goodbye and best wishes.